Good afternoon, everyone. My name is Angela Fawcett. Great pleasure to be with you today for this symposium for the IOP 2021. I'd like to thank Professor Chiaresco for inviting me to join. So my topic today will be procedural learning deficit, dyslexia, and delayed neural commitment. Okay. So I'd like to start by introducing the concept of dyslexia and learning, the automatization deficit hypothesis. So we said in our research that the correct description of dyslexia is specific learning difficulties or specific learning disability. And so dyslexia is some general deficit in learning. So for some reason, it's difficult for dyslexic children to become expert in a task, whether it's a cognitive task or a motor task. And that led to our automatization deficit hypothesis in 1990. Dyslexic children have problem-making skills automatic and need therefore to consciously compensate even for simple skills. So this was an interesting study that we used to look at where the problem arose. So we looked at processing speed, reaction times, and dyslexia. And here we have 5 groups of children, controls 15, dyslexics 15, down to age 8, the controls in black and the dyslexics in stripes, and the tasks built in complexity. So we started with a simple reaction time, simply press a button as fast as you can in response to a tone. And then we had a selective choice reaction, press for the high tone, ignore the low tone, and then we had to decide whether it was a word or not a word. And here you can see that for the first task, simple reaction time, no difference between the dyslexics and the controls. Whereas for the selective choice reaction, the problem arose when they had to actually make a choice, a decision. So the deficit increases directly with task complexity. For simple reaction, no apparent deficit, the same as chronological age, faster than reading age. For selective choice reaction, they're at the level of their reading age controls, although in fact the response is exactly the same. And for lexical decision, they're actually worse than their reading age controls. So we found that the problems, in fact, ran deeper than language. It was more of a processing problem than a language problem. So our next task was to blend 2 tasks together, 2 simple reaction times, to see how dyslexic children would learn in comparison with controls. And here we have over 2,000 trials. First of all, we had to press a button as fast as you can with your hand if you see a flash, and press a button as fast as you can with your foot if you hear a tone. And in blue, we have the hands for the dyslexic on the left-hand side, and in blue again on the right-hand side, we have the processing speed for the foot. And what we want you to see is there were problems with the initial blending. In fact, there were more errors for the dyslexic group, slower final performance and slower learning. And in fact, what the red circles here show on the left and the right is that the dyslexic group, the 15-year-olds, were slower on their hand response than the controls were on the novel foot response. And in fact, the controls were over 30% faster. And we came up with a new way of describing that. So here we're looking at how a child learns, and we could see a climb from a slow climb up to the asymptote where performance improves no further. And for the dyslexic, it seems the difficulties lie at the start, the middle, the end, and in blending the skills together. Here you can see where the difficulties arise. And we came up with a cube root rule. This was that the extra time needed for a dyslexic child to master a task is proportional to the cube root of the time a non-dyslexic child takes. So if it takes 8 trials normally, it's 16 for a dyslexic. If it takes 27 trials, 3 times as long, and if 1,000, 10 times as long. So there are problems at all stages in learning, and so it's more than automaticity. So we came up with an ontogenetic causal chain, how dyslexia would develop between the ages of birth and 8 years old, when it's usually diagnosed. And we suggested there was a problem in the cerebellar cortical loop. So some problem in the cerebellum at birth. It would lead to a balance impairment and also to a motor skill impairment, which would lead directly into writing. It would lead to problems in articulatory skill, one of our most complex motor skills tasks, and that would lead directly into phonological awareness problems, a key deficit for dyslexia. But there's also problems in becoming automatic in skill and knowledge, and that together creates a double whammy. Grapheme phoneme conversion is difficult, recognizing whole words, recognizing orthographic regularities for spelling. And so that impacts on both the reading and the spelling criterial difficulties for dyslexia. And in there we have the main route through from the cerebellum to articulation to phonology, with an impact, of course, on working memory. And here we have our book. Oh, we have strengths in declarative learning. And here we have our book, Dyslexia, Learning and the Brain, which explains our whole program. So that led us to look at the brain, the procedural and declarative memory systems. And there are two different systems, the declarative memory in blue and the procedural memory in red. And declarative is learning facts, whereas procedural is learning how to do something. And the declarative and the procedural memory conspire and compete. So that simply means if you're good at one, then that will take precedence. So for the dyslexic children, they will learn best through the declarative learning, whereas the procedural learning will be impaired. And we suggested a specific procedural learning deficit hypothesis. The core difficulties in dyslexia relate to the language-based component of the procedural learning system, and the declarative learning system is performing at or above normal levels. Other components of the procedural learning system and other neural systems may be, but need not be affected. So let me show you how that fits into the levels of processing the neural. Here we have the neural systems, which falls in between the biological and the cognitive. So we have some unknown genetic cause or causes. We have a cerebellar deficit at the biological level, possibly in other parts of the procedural learning system, especially the inferior frontal cortex. A problem with the procedural learning system. This would show up as a cognitive difficulty with things like automaticity deficits, phonology problems, working memory problems, and speed. And at the behavioral level, that shows up as poor procedural learning, with an overemphasis on control processing and the possibility of secondary symptoms, such as emotional symptoms. If we looked at the different stages and timescales of learning, we found problems at all the stages, but where do they come from? That learning study that I showed you in the beginning took place in multiple sessions over several weeks. So the immediate stage of learning takes seconds, practice takes from minutes to hours, consolidation is overnight. That's a magical process. It happens without any volition on your own part. It just happens by sleeping, and your brain trace, it just becomes better and stronger with a good night's sleep. And automaticity, of course, takes days. So we wanted to look at procedural learning in the brain to show the importance of motor learning. The immediate stage takes many brain regions. The practice takes the cerebellum, the striatum, the motor cortex, the parietal cortex. Consolidation, that's divided into two routes, striatal and cerebellar, with parietal and motor cortex. Again, automaticity, the striatal and cerebellar routes diverge more, again with the parietal and motor cortex. And the corticocerebellar circuit is involved in motor adaptation, and the corticostriatal circuit in motor learning. So here was a study of motor sequence learning. This was in high achieving dyslexic students in Sheffield. And here we were looking at their ability to perform a sequence of key presses. And we were interested in how many they could do in 30 seconds. And we had a study which took place over 2 days. So here you can see that the left-hand panel shows the dyslexic participants learned slower initially, remained slower at the end of the first session, and were slower at the start of the next day. But if you look at it slightly differently here, in terms of effect size, here along the naught line, that's the controls, and their performance. And this is based on the mean and standard deviation of the dyslexic group, showing the differences between combining speed and accuracy. And here you could see that the dyslexic group start very badly with poor performance. In the middle of the day, their performance improves and it's virtually indistinguishable from the controls. But after the consolidation, going away, coming back the next day, their performance has deteriorated again, whereas the controls has improved. A clear loss overnight, showing a basic problem in consolidation for our dyslexic students. So here's our declarative versus procedural circuits we reported in Trends in Neuroscience in 2007. There's a declarative and procedural learning system. That declarative learning problems would lead to generalized learning difficulties. The procedural learning is both the corticostriatal and the corticocerebellar. That affects language and motor skills, leading the language directly to specific language impairment, motor skills to developmental motor coordination disorder, and the corticocerebellar language and motor leading into the motor to ADHD and the language to dyslexia. And of course, there's links between the two systems. And so those are the weaknesses for dyslexia, whereas the declarative learning system will be the strengths. There's growing support for the procedural learning deficit. The declarative memory in dyslexic children shows learning and retention, which is actually better than controls. And a meta-analysis of serial reaction time studies shows consistent effects. Gabay has done a whole series of studies finding deficits in probabilistic and statistical learning in university students with dyslexia and impaired learning of auditory categories, which leads to phonological deficits. They've also shown deficits in consolidation in children and in students, which is greater for letters than it is for motor sequences, even with prolonged initial learning leading to equal performance in the first phase. So reinforcement learning providing a mechanism for phonological deficits. So it does seem to be that there's growing support for this procedural learning deficit that we came up with. So why would there be strengths? Here we're looking at what we call delayed neural commitment. If we look at automaticity, the effects of automatization is neural commitment, a small dedicated cell assembly encapsulated with a loss of conscious access. It's a stimulus response habit. And the upside is it's fast, it's efficient, takes no conscious capacity, and it frees controlled processing, allowing new skills to be built on top. And if we look at bilingualism, for example, monolingual language acquisition shows at 6 months, babies can distinguish sounds in all human languages. And at 12 months, they've specialized onto the phonemes occurring in their mother tongue. This is an example of neural commitment. At bilingual language development, they continue to show a specialization for both their mother and their father tongues up to 12 months. And this gives them advantages in executive function, which is shown to be crucial in learning at around 5 to 6 years, and it also seems to protect against Alzheimer's. So automaticity is fantastic, but does it have a downside? Well, you can have premature neural commitment. So you commit to one component only for complex skill. And that means that it's much harder to unlearn a habit than to learn it in the first place. You have a loss of declarative access. Once the skills are automatized, they're no longer available for conscious access, and you can't integrate that information with other declarative information. It overwrites your previous skills, so your new skills will replace old skills, and you may lose those non-language skills that characterize young children, things like exceptional non-verbal memory and exceptional spatial skills. So here's our delayed neural commitment hypothesis. dyslexic individuals are relatively slow to automatize skills, and they therefore show delayed neural commitment. That occurs for most skills, but especially for language-based ones. While generally it's associated with slower and more effortful processing, it can give advantages, especially where it's useful to maintain earlier skills or valuable to combine two different skills, which don't normally occur within the same time window. The DNC can therefore lead to two crucial advantages: retention of access to pre-linguistic skills and combination of knowledge from two different domains. And so this would lead to a declarative specialization, strengths with facts, an extended sensitive period, allowing extended learning periods into late adolescence and even adulthood, reduced commitment and compartmentalization, which allows greater cognitive processing and flexibility, and more crosstalk between different brain regions and centers to allow more integrative processing. Evidence for that is emerging. Neural commitment is based on the primary mechanism for language specialization in infants. The reading delay, especially the transition from logographic to alphabetic, and then the transition from the alphabetic to orthographic, is very clear in dyslexia, though the visual word form area may never develop fully. There's automatization deficit, as we've shown, and also statistical, procedural, and implicit learning weaknesses for a whole range of researchers. There's no sensitivity to speech sounds at birth, and so no learning in the womb. That's work from Heike Lutonen and Dennis Morfese in family studies of dyslexia. And for some children, the primitive reflexes are not unlearned. And delay in speech milestones, and also in some cases, motor milestones, again from the family studies. Thank you very much. So that's my talk, delayed neural commitment and strengths in dyslexia. Thank you.
Good afternoon. I don't know, of course, whether it's afternoon at your location, but I'm recording this presentation in the afternoon, local Amsterdam time. Before starting, I would like to thank Professor Chiarenza for organizing this symposium and inviting me to participate. My presentation is concerned with letter-speech sound mapping. This mapping is a key factor in learning to read fluently. Most children are able to learn the mappings during the first year of reading instruction, but the automatization of the mappings takes a considerable time, as indicated in the left picture. This picture shows also that children with dyslexia are lagging behind and do not attain automatization levels acquired by typical readers. The right-hand picture illustrates the brain regions that are implicated in letter-speech sound mappings, as suggested by a recent review by Richlan. The studies that I will present are from dissertation work done in my lab. The behavioral studies are by Sebastian Aravena. Those studies are concerned with letter-speech sound mapping in artificial script. The brain potential studies are by Jorge Fraga Gonzalez and focus on the N1 brain potential measure associated with word reading. All studies are posted on the website of the Rudolf Berlin Center for Dyslexia and Related Disorders at the University of Amsterdam. Aravena used artificial script for examining letter-speech sound mappings. The advantage is that it rules out potential differences in the exposure to natural script between dyslexic and typical readers. He used 8 different letters from Hebrew script that are used to create monosyllabic Dutch words and non-words. The letters are used for letter-speech sound training. Aravena used 2 types of training, explicit and implicit computerized training. The screen on this slide is concerned with explicit training. Children hear a Dutch speech sound that they have to associate with the artificial letter presented on the computer screen. This learning of the association is facilitated by a visual cue, in this example the rose. The next step in the training is to use artificial letters for typing in the word they hear via the headphones. This task is again facilitated by a visual cue. And another step is to read the words presented in artificial script. And these words can be natural or pseudo words. The other type of training is implicit and is using a Tetris kind of format. The screen presents balloons containing artificial letters, and the task is to shoot a balloon with the cannon below containing the letter heard via the headphones. This has to be done as fast as possible. In some task blocks, some of the balloons may also contain words in addition to the balloons containing individual letters from the artificial script. One of Aravena's first studies aimed to compare explicit versus implicit training in their effects on several outcome measures relevant for the assessment of dyslexia. The figure presents the procedural details of the study. There were 3 training sessions separated by assessment periods. 1 week after the training session, there was an additional assessment session to assess the robustness of the findings. The results revealed that the acquired letter knowledge was better for explicit relative to implicit training. More importantly, the task didn't differ with regard to the reading of artificial script. Moreover, and most importantly, the artificial script reading was less proficient in children with dyslexia. And finally, the reading of artificial script correlated significantly with the reading of natural script, adding to the validity of the training. The second study, presented here, used the implicit type of training in letter-speech sound mappings in artificial script. Children with dyslexia and typical readers received only 20 minutes of training. And in spite of the brief training, the outcome measures, mapping speed and mapping accuracy, were moderately successful in predicting group membership. Although the results suggest that the brief training falls short of clinical purposes, they nevertheless indicate that this training might be used successfully together with conventional diagnostic procedures in the study of dyslexia. In this study, Aravena evaluated also the implicit training of letter-speech sound mappings in the context of conventional measures used in the assessment of dyslexia. The 2 measures in question are phonological awareness and rapid automatized naming, RAN. The upper panel of the left plot, it can be seen that word reading in the artificial script outperforms both phonological awareness and RAN performance in predicting reading accuracy. And in the lower panel, it is illustrated that word reading in the artificial script outperforms phonological awareness in predicting the speed of word reading. In the right panel, it can be seen that measures derived from the training are doing better than RAN in predicting the accuracy of spelling recognition and better than phonological awareness in the speed of spelling recognition. All in all, it seems that the brief implicit training using artificial script is doing a fair job in predicting reading fluency and spelling recognition in dyslexic children. In another study, Aravena examined the potential of the implicit training in the early detection of future dyslexia. The training was provided to children at familial risk for dyslexia. They should have at least one sibling diagnosed with dyslexia, and another group was composed of children at typical risk. The training was provided at the end of kindergarten, and reading measures were taken 2 years later. The table indicates that the children at familial risk are overrepresented in the lower quartile or decile of the reading scores. The right-hand plot shows that next to phonological awareness, letter-speech sound mapping accuracy derived from the training provides a good predictor of word reading. This finding indicates that the training may contribute to the early detection of dyslexia risk. In a final study, Arafina examined the training as a tool in predicting response to intervention. The intervention consisted of the Lexi program developed by Jürgen Times and others. The focus of this program is on learning the dyslexic pupils to recognize and use the phonological and morphological structure of Dutch words. The program is computerized with the assistance of a tutor and typically takes around 40 weekly sessions of 45 minutes with a tutor and also practice at home. The table shows that Lexi has beneficial effects on reading accuracy and, importantly, on reading fluency that is typically robust against intervention. Spelling improves also. The table in this slide reveals that the combined measure derived from the letter speech sound training explain an appreciable portion of the variance in predicting the intervention success of the Lexi program. These combined measures are doing much better than either phonological awareness or REN. Summing up, the results supported by Arafina indicate that the brief letter speech sound training can be used profitably in the detection, diagnosis, and treatment of dyslexia. Conceptually, the RF findings highlight once again the importance of considering letter speech sound mapping with regard to fluent reading and in the study and treatment of dyslexia. I will now briefly present the results of two brain potential studies conducted by Gorka Fraga Gonzalez. The first study presented to children with dyslexia and typical reading children a visual task with two types of trials presented in separate blocks. One type of trial presented Dutch words and the other type of trial presented strings consisting of symbols. The child task was to identify whether the word or string on the current trial was identical to the one presented on the immediately preceding trial. During task performance, the EEG was recorded for the purpose of extracting the N1 component of the brain potential elicited by the words or symbol string. The N1 component is known to be sensitive to word reading and has been associated with the brain's visual word form area. The left picture of this slide presents the brain potentials focusing on the N1 and its scalp distribution associated with words and symbol strings for dyslexic and typical children. The right-hand plot presents N1 amplitude over the left and right hemisphere for words and symbol strings separately. It can be seen that the N1 to words is more pronounced over the right relative to the left hemisphere in typical readers. This hemispheric difference is absent in children with dyslexia. And in addition, there is no hemispheric difference in N1 amplitude to simple strings. The plot in this slide illustrates the relation between the N1 amplitude difference between words versus symbol string and reading fluency. It can be seen that in the children with dyslexia, this difference is positively related to reading fluency. This relation is completely absent in typical reading children. Now, this slide provides a summary of the results. Word processing, as indexed by N1 amplitude, is more demanding than simple strings. The left hemisphere seems to be more proficient in word processing than the right hemisphere, and this hemispheric specialization is absent in children with dyslexia. Word fluency is indexed by N1 amplitude difference over the left hemisphere in children with dyslexia, but this relation is absent in children that are typical readers. Well, the final study presented here is concerned with remediation, and in addition, it will be evaluated whether the hemispheric difference pattern obtained in the last study can be replicated. These slides present the basic setups of the remediation study. The intervention consists of an adaptation of the Lexi program with a special focus on letter-speech sound mapping, and the outcome measures are the ones typically used in this context. The N170, also known as the N1, is recorded and analyzed as before. This table it's too complex to review all the results, but basically it can be seen that the current Lexi adaptation has overall beneficial effects, and importantly, most notably for the reading fluency measures. And the left-hand plot presents the N170 amplitude results at pre-test. The pattern is an exact replication of the results of the previous study. The right hemisphere N170 amplitude is larger than the left hemisphere one for words, but not for symbol strings, and for typical readers, but not for children diagnosed with dyslexia. And the right-hand plot illustrates the major finding from this study. It shows that the change in N170 amplitude to words over the left hemisphere is positively related to gains in reading fluency attained by the dyslexic children after following the Lexi intervention program. In sum, the Aravena set of behavioral studies indicated that the brief training of letter-speech sound mapping using artificial script is useful in the classification and in promoting word fluency, in the prediction of response to intervention, and in detecting early risk. The two studies from Fraga Gonzalez indicated that the N170 amplitude is suggestive of less hemispheric specialization for word reading in individuals with dyslexia, and provides an index of the beneficial effects of explicit training in letter-speech sound mapping on reading fluency. And collectively, the pattern of findings underscore the importance of letter-speech sound mapping in learning to read. In this regard, the current findings resonate with the claims made by our colleague, Professor Leo Blomert, who presented an invited address at the IOP conference in Budapest, and who sadly passed away much too early. Finally, I would like to thank my collaborators, from left to right, Jurgen Tijms, co-developer of the Lexi program, Patrick Snellings providing linguistic input, and Sebastian Aravena and Gorka Fraga Gonzalez, who both did all the work presented here. Financial support from the Dutch Research Council and the Ewell Institute for Dyslexia and Related Learning Disorders is also greatly acknowledged. And warning, this is not artificial script, it is plain Dutch for thank you for attending.
Hello. So today we're going to speak about the quadratomotor training effects on cerebellar oscillations and focus on the implications for dyslexia. My name is Tal Dutan Ben Susan. I'm the director of the Research Institute for Neuroscience, Education and Didactics of Fondazione Patrizio Pauletti. I'm very honored to take part in this wonderful symposium organized by Professor Giuseppe Chiarenza. So usually when we think of dyslexia, we think of the cognitive deficits characterizing it, such as fluent word recognition challenges or poor spelling or decoding abilities. But there are also emotional aspects related to dyslexia, related to low self-esteem, coping, and many instances of depression. So in addition to registering the brain activity, I like also to interview the participants, and I would just like to give a small example from a report of one of the dyslexic participants that said, my balance is not so good naturally, so it may have improved. There were times I got confused and it bothered me because I felt stupid. In the beginning, I was angry at myself. And in fact, many times in dyslexia, there are also motor deficits, such as problems in tapping, heel-to-toe placement, and rapid finger opposition. So this led scientists to think that the sensory motor deficits that are often observed in different developmental disorders, and especially in dyslexia, could be related to the cerebellum and its functions. And you will hear this in the current symposium, of course. The cerebellar deficit hypothesis of dyslexia by Nicholson and Fawcett describes and says that in the basics of decreased motor skill is a deficit in cerebellar function. And in fact, there are many evidence supporting this. Also, in terms of the connection between the cerebellum to verbal fluency, attention shifting, and the cerebellum, of course, is very important for timing. All these functions could be related to the cerebellar's role in regulating the rate, the force, and the rhythm, and the accuracy of movement, in which it is crucial to control the speed, the capacity, the consistency, and the appropriateness of the cognitive processes. So we can look at the cerebellum as an oscillator, in addition to being a pacemaker. So the possible rationale for the cerebellar involvement in dyslexia could lie in the cerebellar role as an oscillator, producing synchronized activity. There are many findings regarding the cerebellum, and it's important as an oscillator related to theta oscillations, alpha oscillations, and other bands. This led us to the hypothesis that if the cerebellar deficit leads to the motor impairment, which affects the reading, thus specifically structured motor practice could improve reading skills by increasing the cerebellar oscillations. In order to examine this, we chose the quadrato motor training by Patrizio Pauletti, which is a specifically structured sensory motor training. You can see an example here, in which the participant moves in the quadrato space. Quadrato in Italian means square. In the first study, we had 16 participants, 8 dyslexic and 8 healthy controls. Healthy, I mean normal reading controls. Both training groups practiced the quadrato motor training for 28 consecutive days, and we measured their cerebellar alpha activity and reading ability before and after the training. Here you can see the experimental design. The reading task was a single word reading accuracy and fluency task in which single words were chosen. We had different versions, of course, for the pre and post. Here you can see different examples of the words in Hebrew that were chosen from a controlled database for this aim. And we used MEG recordings to measure the alpha power and coherence. So the results. We see that both the dyslexic and the control groups improved their reading following 28 days of the quadrato motor training. In addition, we see that before the training, so in baseline, the cerebellar alpha was much lower in the dyslexic group compared to the normal reading control. And following the training, the cerebellar alpha power significantly increased in the dyslexic group. So these are very novel findings in regard to the cerebellar involvement in dyslexia in terms of the quadratomotor training. So the first thing we see, as I just said, is that the baseline cerebellar alpha activity is lower in dyslexic compared to control. And the 4-week training program enhances this cerebellar alpha activity. And in addition, reading significantly improved. So here, this is a more elaborated model. Until now, we discussed the oscillatory activity, which improves reading following the quadratomotor training. This is considered a faster track, but there are also molecular findings which lead also to anatomical changes related to cognitive improvement following the quadrato, and especially following the quadrato in dyslexic participants and reading abilities. And I will shortly describe some of our results related to this slower path, and especially in relation to pro-BDNF and pro-NGF. So neurotrophins are known to be crucial for neuroplasticity, and we know, for example, that nerve growth factors, so NGF is important for synaptogenesis, and also BDNF can improve and change following training paradigms. So before showing the results related to dyslexia, of course, we do trials in healthy participants, and we demonstrate that following a practice of 3 months of daily QMT, pro-BDNF levels can increase. And this was significantly correlated to increased cerebellar volume. Why is this important? Well, it's important in many levels, but one of them is because saliva is much easier to register and to monitor, and we can measure it in bigger populations. And to know that there is a correlation between the change in the pro-BDNF and cerebellar activity can help us, again, in verifying also the cerebellar hypothesis, and to see which paradigms help in a parallel to the reading and other cognitive skills. Then, of course, we took a case study of a 20-year-old Italian dyslexic participant, which has suffered for many years also from dysgraphia and other very strong deficits. And we practiced with him the quadratomotor training for 10 consecutive weeks. And we see again that the pro-BDNF level significantly increases following 10 weeks of training. And this was related also to improved reading in this participant. And we see that it took 10 weeks, but he succeeded to improve significantly. So these results together support the hypothesis that the cerebellum plays a role in skilled reading and begin to unravel the underlying mechanisms that mediate cerebellar contribution to cognitive and neuronal well-being, following training, of course. So until now, I mostly focused on cortical synchronization, and it's related to reading, but we know also that the cerebellum is very important for timing. So I would like to show you some results related to this shortly, because I know we don't have much time. So we used the time production task, and participants were asked to press a button after a number of seconds that were pre-given to them. So for example, 4 or 8 or 16 or 32 seconds, and then to press the button. And here we also examined it in the context of autism, because we know also that there are cerebellar deficits not only in dyslexia but also in autism spectrum disorder, in which early cerebellar activity has been shown to be lacking and to be correlated with the symptoms of autism, and especially in the case of Asperger. So we know that autism and Asperger are associated with problems in the cerebellar function, and we know that QMT, the quadratomotor training, can enhance cerebellar oscillations. So could the QMT lead to positive outcomes following a longer period of training? And could this be related to improved timing? Here I'm showing you a pilot case study with a 9-year-old child suffering from Asperger, which we trained for 2 months. And we measured, I'm going to focus only on the time production task, before and after the training. And we see that before the training, he was much slower in his time production ability. And following 2 months of training, he reached a very good level of correct time production. In another study, we examined the time production in a group of dyslexic adults, both females and male, and compared to controls. And we saw that longer time production was achieved following a month of QMT in the dyslexic participants, and an opposite trend was in the controls. Together, these results suggest that longer and more accurate time production is related to the quadratomotor training and could be related to enhanced attention. And why am I mentioning this? Because we see that it is not always the case. Not every training is related to improved time production. Now, the last study that I'm going to show you related to timing and to time production is a study in which we compared the quadratomotor training to Aikido expert and to non-active controls. And again, using the time production task, we see that there is a difference between the quadratomotor training and the Aikido group, in which the quadratomotor training is much more accurate in its time production, and actually the Aikido experts are more similar to the non-active controls. But this we can elaborate in another time. The accurate time production was also correlated with improved coordination abilities, again linking us to the cerebellum. In summary, the present result supports the usefulness of integrating training such as the quadratomotor training. They support the cerebellar hypothesis of dyslexia and suggest that the quadratomotor training can aid in developing cognitive functions such as reading and time production, as well as well-being in general populations and especially in dyslexia. Here are some of the main related publications. I would like to thank my group and thank you for your attention.
Hello everybody, I'm Thomas Lachmann. Many thanks to Giuseppe for organizing this session and for inviting me to present here our recent MMN study, which was an international collaboration between the Max Planck in Leipzig and the universities in Bergen, Jerusalem, and Kaiserslautern. We decided to have Tatsuya, who essentially conducted the experiments, to present the data. Thank you very much.
Hi, my name is Tatsuya Daikoku, an assistant professor in the University of Tokyo in Japan. The title of this study is Neural Correlates of Statistical Learning in Developmental Dyslexia. The brain can identify statistical regularity in sequential information, referred to as statistical learning. Statistical learning is thought to play a crucial role in early language acquisition. For example, even 8-month-old infants can learn probability of specific syllable transitions, an ability which enables them to detect word boundaries and isolate single words out of fluent natural speech. Developmental dyslexia impairs reading comprehension and spelling and affect approximately 5% of the population and arise from phonological deficit. Recent evidence suggests that auditory statistical learning is also impaired in both children with dyslexia and adults with dyslexia. However, surprisingly few neurophysiological studies have assessed how dyslexia affects the neural processing underlying statistical learning. Electroencephalography can be used to measure neural activity during statistical learning, with EEG data often being more informative than observation of behavioral effect on statistical learning. Mismatch negativity effect observed 100 to 200 milliseconds after stimulus onset can consistently capture statistical learning effect. Our recent study designed a novel experimental paradigm involving toe sequences that can include both location deviant, consisting of stimuli from unexpected direction, and statistical deviant, consisting of stimuli with low likelihood of following the stimuli presented earlier in the sequence. We found that both statistical and location deviant elicit prominent mismatch negativity responses, approximately which is referred to as statistical mismatch negativity and location mismatch negativity. However, no study have demonstrated how individuals with dyslexia represent statistical learning, statistical mismatch negativity, and location mismatch negativity. Therefore, in this study, we investigate how dyslexia affects mismatch negativity responses to auditory sequences, including both statistical and location deviants. Assuming that dyslexia adversely affects the inference of sensory statistics in the auditory cortex, we also assume that statistical and location deviance would elicit weaker mismatch negativity in participants with dyslexia compared with control participants. Confirming this hypothesis would provide evidence that the mismatch negativity partially represents auditory processing dysfunction in individuals with dyslexia. Our study samples include 17 adults with dyslexia and 19 control adult participants, who all met the 4 criteria, that is, German as native language, right-handedness, no history of neurological or audiological disorder, and no diagnosis of general or specific language impairment. And further, no formal musical training for more than 5 years outside of regular school lesson. Spelling skills were assessed with German spelling test. Text reading speed and reading comprehension skills were assessed with LVGT test. Relative to control group, the dyslexia group had lower average score for spelling ability, reading comprehension, and reading speed, as shown in the table of this slide. However, the two groups were comparable in terms of age and intelligence. Further, both groups had IQ score in the normal range. Regarding experimental paradigm, the participants were exposed to continuous stream of 400 sound triplets in which a few triplet endings were location deviant. That is, presented from unexpected speaker direction, or statistical deviant, that is, a low transitional probability given the triplet first two sounds. In more detail, figure A shows 4 types of triplets generated from 6 different sounds. Each triplet consisted of a root containing 2 conserved sounds and a triplet ending with high or low transitional probability given the triplet root. Each triplet root has a 50% probability of occurrence, regardless of the ending sound of the previous triplet. Figure B shows example of the possible triplet sequences, including standard triplet, triplet with a statistically deviant ending or location deviant ending, and a triplet with both statistical and location deviant. They completed a multi-stage experiment with 6 blocks while undergoing EEG monitoring. Each of 6 blocks includes an exposition phase involving passive listening and subsequent behavioral testing. During a behavioral testing phase, the participant listened to a paired statistically deviant and standard triplet. After each pair of triplets, a participant was asked to choose which triplet in the pair sounds more familiar or not. First, we examine whether dyslexia affects mismatch negativity or other event-related potential responses to location deviant. Location deviance elicits a P120 followed by a location mismatch negativity in the anterior frontal area. The location mismatch negativity appears in both dyslexia and control group, but has smaller amplitude in the dyslexia group. Next, we examine whether dyslexia affects event-related potential responses to statistical deviant. Statistically deviant triplet ending elicits a P120 followed by a statistical mismatch negativity, which was maximal over anterior frontal electrodes. Statistically deviant triplet ending elicits P120 in both groups. However, they elicit statistical mismatch negativity in the control group, while no statistical mismatch negativity in the dyslexia group. The performance in the behavioral testing phase also revealed no effect on response accuracy. Response accuracy did not correlate with confidence rating in either the control group or the dyslexia group. Similarly, response accuracy did not correlate with dyslexia test score. Here is the discussion. In this study, we assess the relationship between dyslexia and event-related potential responses to a continuous stream of sound triplet, in which some triplet endings were either locationally or statistically deviant. We found that the statistically deviant triplet ending elicits small statistical mismatch negativity, and that location deviant triplet ending elicits larger location mismatch negativity. The statistical learning and basic auditory process were reflected in statistical mismatch negativity and location mismatch negativity, respectively. The location mismatch negativity is the responses to sensory memory operations that are instantly updated after new information is obtained. On the other hand, statistical mismatch negativity relies on memory representations formed from the implicit knowledge of the sequential statistical structure, which go beyond simple sensory memory. Notably, the statistical mismatch negativity effect elicited in our experiment were prominent in the anterior frontal area of the brain, but the location mismatch negativity effect was broadly distributed from central to frontal areas. This may imply the difference in neural processing between statistical mismatch negativity and location mismatch negativity. We also detected group difference, that is, compared with the control group, the participants with dyslexia exhibit weaker location mismatch negativity effect. They also exhibit no statistical mismatch negativity effect. Behaviorally, there were no significant between group difference in the ability to learn the statistical characteristic of stimuli. Our findings show that the neural mechanism underlying the statistical learning mismatch negativity, as well as location mismatch negativity, can be impaired in the individual with dyslexia. It has recently been considered that the domain general statistical learning deficit, rather than specific to phonological reprocessing, may underlie dyslexia. For example, individuals with dyslexia weaken domain general statistical learning ability across sensory domains such as auditory and visual stimuli. Further, statistical learning deficit in dyslexia is not limited to speech stimuli but occur in non-speech stimuli. The present study explored effect of deviation from prediction based on the physical and statistical property using non-speech auditory stimuli. Our findings show that the statistical learning process as well as basic auditory processing are affected in individuals with dyslexia. So this suggests that the neural processing of statistical structured property is also impaired in people with dyslexia. Further, both location mismatch negativity and statistical mismatch negativity were preceded by P120 responses. Compared with control, the participant with dyslexia exhibited no difference in P120 between location deviant and standard. Further studies are therefore necessary to elucidate whether the neural basis of statistical mismatch negativity and P120 components elicited by statistically deviant stimuli are distinguishable from those of location mismatch negativity effect and P120 component elicited by location deviant stimuli. In conclusion, our findings lay forth evidence that location deviance elicits larger classic mismatch negativity, which was larger in control than in individuals with dyslexia. Statistical deviance elicits statistical mismatch negativity in controls, whereas individuals with dyslexia did not exhibit any statistical mismatch negativity. Our findings offer novel neurophysiological insight into the neural mechanism underlying dyslexia and indicate that the neural mechanism underlying statistical learning can be impaired in dyslexia. These insights may have application related to the detection and treatment of dyslexia. Finally, this study was supported by Japan Society for Promotion of Science, the German Israel Foundation for Science Research and Development, and Nakatani Foundation in Japan. Thank you very much for your kind attention.
This presentation deals with the study of the direction of information flow in dyslexic subjects in comparison with children who have only a simple reading delay. Numerous clinical observations have reported that subjects with developmental dyslexia have difficulty in motor organization when they execute neuromotor tasks, both simple and complex. These difficulties in execution of motor tasks are associated with minor motor neurological signs as dysrhythmia, synkinetic, or mirror movements. More recently, Nicholson Fawcett reported that dyslexic children have difficulties when required to undertake fast, fluent, overlearned skills or novel skills that involve the blending of two actions, and their performance after extensive practice is slower and more error-prone. These motor impairments have been related with a disturbance in time organization in the performance of a motor skill. These multiple clinical and behavioral observations are further confirmed at the neurophysiological level. Linus supports the hypothesis that at the base of dyslexia, there may be a neuronal dyschronia that lead to inefficient integration of information from various brain areas. The studies of movement-related potentials recorded during the execution of a self-paced, bimanual, ballistic, skilled task demonstrate that dyslexic children had a significantly reduced BP onset and amplitude. This potential seems to reflect the ability to program a goal-directed movement by selecting all those idiokinetic elements necessary and essential for executing a goal-directed motor act, or in other words, the capacity to represent the sequence of movements to be performed. The BP is followed by the MCP, motor cortex potential, which is also reduced in amplitude and with longer latency. These potentials seem to be an index of reafferent peripheral activity coming from muscle and joints. This potential is followed by the N100, the expression of the early stage of visual processing of the brain response to the visual stimulus, and also this potential is increased in latency. The P200 associated to reafferent activity is also reduced in amplitude and increased in latency. After movement completion, a larger positive potentials with a latency of 460 milliseconds, denominated SPP, skilled performance positivity, with the central and the parietal scalp distribution appears on the scalp. This potential is present in the parietal areas, but of reduced amplitude and absent in the central and the frontal areas. The SPP is absent during unskilled task and when adequate feedback is not provided to the subject. From a chronological standpoint, it may be said that the SPP coincides with the subject's awareness of the success or failure of his performance. This positivity appears when the subject looks for information about his outcome, that is to say, information relevant to the efficiency of his psychomotor pre-programmed organization. The knowledge of the outcome is likely to be used to influence future actions. We can suggest that dyslexic children have a reduced capacity to learn from the errors. Most of them, they are not aware of their reading errors. Taking all together these results, we may conclude that the subjects with the dyslexia do not only suffer from a phonological or a gestalt deficit, but also from a praxic disorder in which praxic abilities such as motor programming, sequential, and sensory motor integration and evaluation processes are somehow defective in dyslexia. These results were confirmed by the brain potentials associated with the self-paced reading aloud. Based on the spatial temporal characteristic of these potentials and their relationship to electromyographic activity and performance, it has been proposed that there are 4 successive time periods: preparatory, pre-lexical, lexical, and post-lexical. And these are the potentials associated and characteristic of each period. The Brashaff potential, the motor cortex, N1, P1, the visual response to the letters appearing on the screen, the potentials associated with the reading, and then also P600 related to post-lexical period. The comparison of normal and dyslexic children showed that in all periods there are many areas involved in reading aloud that are dysregulated. In the preparatory period, the BP is reduced in fronto-central areas. In the pre-lexical period, N1, P1, there is a hypoactivation of the left cuneus and the left angular gyrus and the hyperactivation of the left temporal choral area. During the lexical period, when N2, P2, P2B, and the other potentials appear, there is a hypoactivation of left supramarginal gyrus, medial precuneus, medial posterior cingulate, occipital lobe. And during the post-lexical period, we found hypoactivation of the medial precuneus and occipital gyrus. A defect of an excess of absolute power in the various frequency bands in different brain areas have been frequently reported by many authors. Using a quantitative EEG Very recently, Bosch and Bayard, comparing the subjects with the phonetic dyslexia, had significantly very recently, Bosch and Bayard, comparing the subjects with the dysphonetic dyslexia with the subjects with the non-specific reading delay, demonstrated that the subjects with the DD had significantly greater activity in delta theta bands in the frontal, central, and the parietal areas bilaterally, compared to children with NSRD. We can conclude dyslexic children show a timing deficit or dyschronia in different brain regions, evident both in the temporal and the frequency domain. Lu et al., using tractography, reported that the network connecting the left occipital temporal cortex and the temporoparietal cortex had decreased the streamlines in dyslexic children, suggesting a disconnection in a local subnetwork in the left hemisphere in dyslexia. fMRI studies have highlighted the 3 left hemisphere areas, which reveal an alteration in subjects with dyslexia. These regions are the parieto-temporal region, the inferior frontal gyrus, the occipitotemporal region, including the visual word form area. Hypo and hyperconnectivity have been observed in subjects with dyslexia in the occipitotemporal areas, in the frontal lobes, and in the central parietal cortex. These studies are based on measures of functional connectivity, such as coherence, which do not allow to infer effective and directed connectivity. The present study overcomes this limitation by examining the effective brain connectivity in dyslexic subjects compared to a group of subjects with non-specific reading delay. The hypothesis is that the timing defect or dyschronia should be reflected also in the effective connectivity, and the subjects with developmental dyslexia have a different pattern of information flow compared to the group of children with the non-specific reading delay. For this purpose, the isolated effective coherence between data-driven selected regions is used as a tool to quantify directed effective connections. The reason for studying these 2 groups of children is based on the fact that the non-specific reading delay has not received special attention neither by clinicians nor by researchers. Frequently, these children remain undiagnosed or confounded with dysphonetic dyslexics until they are in a secondary school. The entire sample consisted of 771 subjects, of which 51% were dysphonetic dyslexics and 14.6 had no specific reading delay. The subsample consisted of 169 dysphonetic dyslexia, 36 non-specific reading delay with EEG studies. For reason of time, I cannot go into full details of the method and can only pick out a few points. An entire symposium organized by Bosch Bayard is dedicated to this method. I recommend you to follow this symposium for those wishing to deepen the subject. After editing the QEEG for artifacts, transformation to the source space and the summarization of the sources to the 9 regions of AAL Atlas were obtained. Then, data-driven procedure was applied to select the interesting areas for connectivity analysis. After correlation analysis, the most significant ROI were chosen. The next step was the calculation of the causal information flow among the 17 ROI by means of isolated effective connectivity and the linear mixed effect model was used to find the most significant differences of the isolated coherence between the two groups. This slide shows the isolated coherence differences between dysphonetic dyslexia and non-specific reading delay. Arrows in red color indicate that isolated coherence information flow between two areas is higher in the D group than in NSRD. Arrows in the blue color indicate that the information flow between two areas is higher in the NSRD group than in the DD group. In each line, there are annotated the frequency band in which the differences were more significant. This slide shows the significant differences in functional connectivity between DD and NSRD groups summarized by bands obtained by the isolated coherence procedure for P minus 0.01 corrected by permutations. Negative values, the blue colors, mean that the connectivity marked by the arrow is greater in the NSRD group. Positive value, red and yellow palette, on the contrary, mean that the connectivity is greater in the DD group. The arrows indicate the direction of the causal influence. In the NSRD group, the left Rolandic operculum is more active than in the D group. Most of the blue arrows appears in the beta 2 and gamma band. Penolazzi et al. Have observed significant improvements in the beta band at the posterior site in a group of dyslexic children after receiving phonological training for 6 months. In the NSRD group, the left thoracic operculum sends more information in the beta and gamma band to a big number of structures: right angular gyrus, superior and inferior parietal gyrus, right postcentral gyrus, and right fusiform gyrus. All these structures play important roles during the execution of reading tasks. This increases the connectivity of the left Rolandic operculum, which can be considered as a hub, may explain why the NSRD group is more efficient than DD. On the other hand, the left calcarine sulcus is very active in the D group from sending information to parietal and temporal areas bilaterally in the delta, theta, and alpha band. Our causality results show a more active connectivity in the D group from the left calcarine sulcus and the right lingual gyrus, part of the visual system, to other regions of the brain. Significant differences associated to connections flowing from the left calcarine occur in almost all frequency bands, but very importantly in the delta band to the right postcentral, the right supplementary motor area, and the left paracentral lobule. These are almost the only connections that occur in the delta band. We hypothesize that the delta band may be associated to less efficient dysfunctional or even pathological connections. The increased connectivity of the calcarine visual areas in these phonetic subjects, IDEST subjects who have a deficit of auditory word analysis abilities, confirms Boder's model, according to which these phonetic subjects are more prone to use the visual channel, that is, they read by sight, rather than using their auditory deficient channel. The only connection coming from the left calcarine, which does not implicate the delta band, is towards the right angular gyrus, which occurs in the theta and alpha band. It has been shown that the angular gyrus is active during numerous verbal tasks, less active in dyslexic during rhyme detection, and more active in dyslexic during orthographic identification. In conclusion, we may affirm that this study represents the first attempt to demonstrate which type of EEG connectivity exists in dyslexic subjects, using the classification in subtypes proposed by Bodel's model. These results show dysregulated flow of information in both time and the frequency domain. I wish to acknowledge with deep gratitude Jorge Bosch Bayard, Rolando Biscay, Pedro Valdesosa, Ala Evans, Katia Girin, and Valeria Peruso. Without their collaboration, this latest work would not have seen the light. Thank you very much.